In this video I want to talk about Python packages, where we've got several different files of Python code with a bunch of different functions in them that call each other in kind of a bit more of a complicated pattern than we've been talking about previously. And as an example of this, I'm going to use a repository with some code for playing noughts and crosses in Python. So here's the repository here, github.com neilstricklandox, and you can see there's a few files here. We've just got double score init double_.py, that's a special one, and then there's 5 more files of different kinds of Python code, and a readme and gitignore file. So we need to clone this repository, so as we got the code on the computer we're using just now. So you have to go to this green button here which says code, and we'll select the HTTPS URL. I'll maybe discuss a bit later about what's the difference between these things, but we're going to stick with the HTTPS at the minute, and we just click this little button here to copy the URL. Then we're going to go back to VS Code. We're going to open a terminal, and then we type git clone, and then we copy in the URL that we just had. Okay, and you can see that here this creates this subfolder called OX, which has all those files in it. We've also got a separate notebook here. So incidentally, note that mostly we've been using Jupyter notebooks with extension .ipynb, but here we've, as is kind of usual for packages, we've done it in a sort of more traditional way with Python. These are just Python files that solely have Python code in. They don't have any markdown cells or anything, and they have extension .py. But that means it's less convenient to interact with them. So we've got a separate file here that's outside the repository that's called tryox.ipynb. So this is a notebook. This will call the functions that are in the repository, and it's just a convenient way to run things and experiment with them. So the first line in the notebook is to import OX. Okay, so this just execute that. Okay, so that's calling the files that are in here. So import OX. Normally we do import. We import packages that have been installed using pip or something, and they're sort of stored in some other folder. It's not so immediately visible. But also, you can also import stuff if it's just kind of in the folder you're working in, right? So more precisely, we're in this folder here that's called trygit, and the OX is a direct subfolder of that, and our tryox notebook, that's in the trygit folder, and so because the top, the OX is kind of in the same folder as the tryox.ipynb, that the import will work as you might expect. Okay, so we're importing that code, and let's just see the kind of thing that we do with it. So I'll run this block of code here, and you can see, so it produces a diagram showing a game of noughts and crosses and saying that player X wins. And so let's have a look at what's going on here. So we're calling this function ox.playgame, which will be defined in one of these files we'll look at in a minute. And it's got ox.randommove, ox.randommove. So this basically means we've got two players, the O and the X, who are just playing random moves against each other. They are not so. They're random in the sense that they are selected amongst legal moves, right? The random move function is set up so that it won't play in a place where there's already a counter. But apart from the fact that it plays in an empty spot, it chooses which empty spot to play in a completely random way. And then we've got this additional argument, return moves equals true. Okay, so then we've got a line here to print a message about who won, and print the moves. Okay, so we've got return moves equals true. That means that the return value of this function will include a record of what the moves were, and that's this thing here. So this says that this means that the O played in spots 3, 6, and 7, and the X played in spots 4, 0, and 8. Okay, so what are these? I mean, the positions are numbered in the obvious way as 0, 1, 2, 3, 4, 5, 6, 7, 8. So the O's, you can see that's 0, 1, 2, this is in position 3, and 4 and 5, and position 6 and 7. So yeah, the O's are in positions 3, 6 and 7, and the X's, this is position 0, that's position 4, that's position 8. So we've got, and so we've called here the function showboard ASCII, which just produces this little plot. This is just like a string, which is kind of like a string representation of the matplotlib diagram, showing the x's here. Notice, incidentally, the x's are kind of in a dark blue because player x1, and the o's are kind of slightly faded. That's to indicate that player o lost. And in the ASCII representation, you've got a hash mark for the blank squares, capital X for the dark blue x's, and a little o for the kind of faded out o's. Okay, so that's what that does. So that's with the two players playing randomly against each other. And then and here's another version. Okay, so this one, we're actually out. You can see up the top we've got a box in which we can input something. We have to enter our first move. Let's say we'll play in position 3. Okay, and now you see we played in position 3, which is that O there, and then our opponent is playing randomly, and the opponent plays in position 0 here, and so we've got an X there. Okay, so let's play in the middle now. So position, that's around 0, 1, 2. O is in the position 3. So let's put an O in the middle, which is position 4. And then because our opponent's just playing randomly, they're not doing anything very intelligent, they've just played up in the top right corner, and so we can win by playing in position 5. So we do that, and now we get, because we've called the OX.showBoard thing, it produces this matplotlib diagram showing how the game progressed. So let's maybe have a bit of a look at some of the code for this. Okay, so we've got this file init.py. Okay, so that just has a small amount of kind of real code in it, but mostly it's just organizational. It's kind of listing this. We define this variable all double underscore, which is a list of the other files that need to be imported. It's kind of, when we import OX, it's automatic that we import the double underscore init thing. But then we don't automatically import any of the other files unless they're listed in this double underscore all thing that's listed here. Then we've got this setup function which defines a few global variables. So we've got these global variables: board, wins, EE, triple E, corners, edges, opposite, empty board. These are all variables that we want to set up to be used by the rest of the code. So board is just range 9. That's kind of 0, the list consisting of 0 up to 8, which is the possible positions on the board. Because you see, we're representing a board generally by things just by lists of length 9. So corresponding to the 9 spots on the board, 0 being the top left, 1 being the top middle, 2 being top right, and so on. Then we've got this array here that's called wins. So what's this about? So let's look at this first line here. So you've got a 1 in position 0, and then in position 3, and then in position 6. So what's these ones, right? So the 1 in position 0, that's the top left, and then in position 3, that's the left-hand end of the middle row, and position 6, that's the left-hand end of the bottom row. So the spots that you've got here in this first thing here, those correspond to the spots in the first column of our noughts and crosses board. And the point being, of course, if you fill those 3 spots, spots 0, 3 and 6, then that means you filled the left-hand column, and so you've won. And whereas this second thing here, this is positions 1, 4, 7, so if you played in spots 1, 4 and 7, that means you've got the middle column, and so you've won. So again, so each of these rows in this wins thing, that's kind of gives you a set of 3 spots, where if you've played in those 3 spots, then you've either got a full row or a full column or a diagonal, and so you've won the game. So this wins table is kind of basically including the rules about who that encodes the rules about who wins. And then this EE is basically the identity matrix, 9 by 9 identity matrix that we're going to use for various purposes. And then triple E is kind of a similar thing. This is a it's a kind of 9 by 2 by 9 by 2 array. Which in the EE, right, is a 9 by 9 array, and then in the ith row of EE, you've got a single 1 in position I. And the triple E thing is kind of the same. In position I, comma j, we've got a 9 by 9 matrix, and the 9 by 9 matrix that you've got in position ij is the one that has a single 1 in position ij and 0 everywhere else. So that'll be a kind of convenient thing to use in later functions. Then we've got these two things called corners and edges. So corners I is 1 if the position I is the corner of the board. So the corners of the board are positions 0, 2, 6 and 8. So we've got 1s in here in position 0, 2, 6 and 8. And the kind of middle edge positions are in these slots here. That's 0, that's position 1, position 3, position 3, position 5, position 7. Those are the middles of the various edges of the boards. And then the position opposite, so opposite, the top left corner is position 0, bottom right corner opposite it is position 8. So this little array opposite kind of tells us which squares are opposite which other squares. And then finally, we need a kind of thing that encodes the empty board. So so we need to understand how the board positions are encoded. So maybe we can, if we go back to here where we actually kind of played a game, and so let's enter PQ. So PQ, this is the array that encodes the final position of the board, and so you see it's a 9 by 2 matrix, and so the left column corresponds to what's happening for the O's, and the right column corresponds to what's happening for the X's. So here you see you've got 1, 1, 1 in positions 3, 4, 5, and those correspond to these O's here. And the X's, you've got a 1 in position 0 and a 1 in position 2 corresponding to that X and that. So this is how we generally encode a state of the game. You've got a 9 by 2 matrix, and in the left column you've got some 1s to indicate the positions of the O's, and in the right columns you've got some 1s to indicate the positions of the X's. Okay, and so for an empty board you've just got a 9 by 2, haven't started playing yet. You've got a 9 by 2 matrix of zeros, and that's what we're setting up here. So we run this setup function to set all these level variables. So we didn't really need to define a function. We could just have had these lines on their own, but somehow it's kind of tidier to wrap everything up into a function. Okay, so then we've got a bunch more files. Let's look first at this file called analyze.py. This contains various functions for analyzing the logic of the game. So we've got this function add_o and add_x, which either adds an O or an X to the game state. So PQ is going to be one of these 9 by 2 matrices, and representing a state of the game, and we want to add an O in position I. And so remember the O's are recorded in the left-hand column of this 9 by 2 matrix. So the correct thing to do to add an O in position I is to set PQ I, 0. In other words, row I in the left-hand column, we set it equal to 1. And to add an X in the position I, we go to the ith row of the first column of our game state matrix and put a 1 there. Then we've got this function hasWin, which is supposed to tell us whether the game's been won. So PQ is the game state. Player is either going to be, player can be 0 or 1 or none. If player is 0, then we check whether the player placing the O's as 1. If player is 1, then we check whether the player placing the X's as 1. If player is none, then we just we check whether either of those things is true. In other words, we check whether the game is finished because one or the other player has won. Okay, and it turns out. So how can we check this? We've done this in a kind of slightly slick way here. We're taking this matrix wins, the wins matrix, and we're multiplying it by the jth column of the PQ matrix. PQ is a 9 by 2 matrix, wins is a 9 by 9 matrix. We can multiply them together to get a 9 by 2 matrix. So what's that really doing? It goes. You look at each kind of pattern. Set of places which could cause a win, and you count how many of them have been filled with those. That's what this matrix multiplication does for you. And so, if in any of these guys, if any of these guys you've got a 3, that means that all 3 of the spots in that particular winning pattern have been filled with those. So that means that the player O has won. So we've got this W here. So W is just going to be a matrix of it's going to be a vector of length 2, and W0 is going to be it's a matrix, but a matrix of true-false values. So W0 is true if player 0 is 1, W1 is true if player 1 is 1. If the player argument is none, then we're supposed to check whether either of these is true, so we do W0 or W1, otherwise we just check the win record for the relevant player. So that's one thing, and then we've got this function called plays. So this gives us the list of available spots. So for technical reasons, we've included the player argument. We're not actually using it. Here n is going to be the list of spots in which we're allowed to play, and we just kind of walk through from I is 0 up to 8, and we check if the spot is empty. So remember. PQI, 0 will be 1 if there's an O there. PQI, 1 will be 1 if there's an X there. So we check if there's no O and there's no X. In that case, the spot is empty, and so we append it to our list of empty spots, and then we return the return. There's a bunch more functions here that do similar kind of analysis. Then we've got this players. So players, this kind of this defines 3 different functions. Each of which is of the same type. These are things that can be used to sort of play the game. So you can play randomly. So there's this random move function, and it has 2 arguments. There's the PQ, which specifies the current state of the game, and player, which specifies whether player is 0 if we're going to place an O, player is 1 if we're going to place an X, so all it does is it uses this plays function, which is going to tell us the list of available empty spots, and we make a random choice of one of those empty spots, and we return it. That's what we normally do, because there's a little bit of extra code here. If sometimes we're not going to return a random move, we're just going to return none. That's if it wouldn't make any sense to return a random move. So that's either if someone's won already, if either the O or the X has already won, then we don't return a move. And also if the board's already full, board could be full with no one having won. If there's a draw, in that case we also return none. So that's and then that's the random move function, and there's the suggest move function, which actually implements the kind of standard algorithm for optimal play. This suggest move function is basically guaranteed to win or draw, and then there's the input move function, which just kind of asks the user to enter a choice of move. So we've put code. So these 3 sort of similar functions. So we've decided to put them all together in a single file. We could have combined everything just into a single file, but it's sort of natural to put similar groups of functions together. So we had this analyze file, which contains all the different functions for analyzing the state of the game. And then we've got the players file, which defines the random move player, the suggest move player, and the input move player. We've got the show file, which defines the showboard and showboard ASCII functions. The showboard function does a matplotlib picture of the board, and the showboard ASCII function generates like a little string picture, which kind of shows the same information but without having to use matplotlib. And then we've got the play thing. So this defines the function play game, which just give it 2 players, which could be the random move player, the suggest move player, or the input move player, and then it runs a game like that by calling those players in turn, and then it returns some information to say what's the end state of the game and who's the winner. So it's just a little bit of a walk through how we organize a Python package with a bunch of different files. There's also a bit to say about these kind of lines here, which say _all. So again, each of these files, there's certain functions. I mean, certain functions that you want to be available sort of outside the file itself. So we're going to list all of those with this _all directive here. So this has the effect that once we've imported this file, then everything else is going to be available. Then we also want to import some other stuff from the other files. Right here, in order to do the random move thing, we need to know which spots are empty. So we use the plays function that we defined elsewhere. But we need to kind of have an actual directive here to make sure that function's available. The plays function was defined in the file analyze.py. So we have this thing here. We say from.analyze import a bunch of things including plays. So that's necessary to make sure that the plays function is available in this file. So this is the kind of thing you have to do when you've got your code separated into different files, and they have to refer to each other. One file has to refer functions that were defined on the other file, and we do need to have these kind of import things here. And notice, remember, you've seen a bunch of import things where we import stuff from packages that were, which were installed using pip, and for those, we don't have to do this dot thing. But when we're doing the kind of thing we're doing at the minute, where we're defining our own package and we're sort of cross-referring to other stuff that's in the package that we're currently defining, then we have to have these little dots to indicate that that's what we're doing. So we do from dot import triple E. That imports the triple E thing that was defined in the init file, and then from dot analyze, which refers to this analyze.py file, we import some stuff that was defined there. And from .show, which was refers to this file show.py, we import the function showboard ASCII. Why do we do that? That's because if we're doing the input move thing, we have to show the user the current state of the board so that they can decide where they want to play next. So we've got the showboard ASCII function is called from inside the input move. And so in order to make sure the showboard ASCII thing is available, we have to import it next. So, and that will be enough for this initial discussion of Python packages.